Let's work an example using what we know about the derivative of sine and cosine and using what we know about the quotient rule. This example says find f prime of x for f of x equals this quotient. And this quotient has sine and cosine in the numerator and cosine in the denominator. So not only are we going to use the quotient rule, we're going to use what we just learned about the derivative of trig functions. So f prime of x, the first thing I'm going to use is the quotient rule, bottom, as it's given to me, d top. Now I need the derivative of positive sine of x plus positive cosine of x. We said the derivative of sine of x was positive cosine, and we said the derivative of positive cosine was negative sine. See how confusing that's going to be getting? Make sure you get those SIGN signs, positive or negative SIGN signs, correctly. The derivative of positive sine is positive cosine. The derivative of positive cosine is negative sine. So there's bottom d top minus top d bottom. The derivative of positive cosine is negative sine. All over bottom squared. Remember, in trig functions, we write the squared before the angle measure. So we know the whole expression is squared. There's f prime. Now we could distribute and clean it up and watch our SIGN signs very carefully, but they didn't ask me to do anything but find f prime. I'm done. Walk away. Never simplify unless you have to. Find the equation of the tangent line to y equals the cosine of x at x equal pi. We need the slope at the point of tangency, and we need the point of tangency, and we're going to plug that into y minus y1 equals the slope times x minus x1. That's what I have so far. Now I need to fill in the blanks here and here. So first of all, let's find y prime of x. Always, I'll repeat it again, find your derivative in your variable. Then plug in your x value. There will be points on free response at this step, and there'll be points attached to this step. If you jump straight to this step, you're losing all those points. Show the derivative in the variable first. So the derivative of positive cosine is negative sine. When I plug in the x value of pi, my slope is 0. Now I know I have a horizontal tangent line. The equation of that line will be y equals some constant. And that constant will be this y value. Why? Because this is the point of tangency. The point of tangency lies on the tangent line. So I need that y coordinate. How do I find it? That is y evaluated at pi. I'm going to put pi into my function. That's going to give me my y value. So the cosine of pi is -1. This cleans up to y plus 1 equals 0. So there is the equation of the tangent line. 2y equals the cosine of x at x equal pi. Given the function, the positive tangent of x, we're going to use the quotient rule, and the fact that we know an alternate definition for the tangent of x is the quotient sine of x over cosine of x. That's why we're going to use our quotient rule to prove the derivative is indeed the secant squared of x, or secant of x quantity squared. So the quotient rule, bottom, d top. The derivative of positive sine is positive cosine. Bottom d top minus top d bottom. The derivative of positive cosine is negative sine all over bottom squared. Well, how is that secant squared? Well, look at your numerator. Clean your numerator up. Cosine times cosine is cosine squared. Negative sine x times negative sine x is plus sine squared of x. All of that over equivalently. That is the bottom squared. I hope you see that. In trig, we write the exponential value in front of the angle measure so that there's no confusion, because the cosine of x quantity squared is different than the cosine of x squared. And so to avoid this confusion, we write the squared term in front of the angle measure. So, do you recognize that as the Pythagorean theorem? Do you recognize that that equals 1? And 1 over cosine squared is indeed secant squared. The derivative of tangent of x is secant squared of x. And we've just used the quotient rule with the alternate definition of the tangent of x. Let's use the fact that we know the derivative of tangent is secant squared of x to work this example. Find the equation of the tangent line to the graph of y equals the tangent of x at the point pi over 4, 1. So we need the derivative at the point pi over 4, and we need this point. We're going to plug that in. We're going to get y minus y1, well, they gave us y1, we know it's 1, equals y prime at pi over 4 times x minus x1, the point slope form. It's what we'll exclusively use. So in order to find y prime of pi over 4, I must first show y prime of x. We said we recognize that as the secant squared of x. In this context, because of our exact values, it's probably going to be easier to write secant squared as 1 over the quantity cosine of x squared. Now, let's plug in our exact value into that definition. We have the cosine of pi over 4 quantity squared. That is 1 over, the cosine of pi over 4 was positive root 2 over positive root 2. That's getting squared. This is 1 over root 2 times root 2 is 2. 2 times 2 is 4. This is a compound fraction. I'll reduce 2/4 to 1/2. Remember, I take the fraction that is in the denominator and flip it and multiply it straight across. So the slope of the tangent line at the point of tangency for this function is 2. The equation of the tangent line is given right here, point slope form. Do not be tempted to turn it into slope-intercept form. We don't need to do that. Number one, it's a waste of time. Number two, we're highly likely to introduce algebra error. Walk away. Lastly, let's talk about the derivative for f of x equals the secant of x. Once again, we're going to use our quotient rule. We're going to use our alternate form for secant. We recognize secant is 1 over cosine. We're going to use the quotient rule to find the derivative. Bottom, d top. What's the derivative of a constant? 0. Minus top, d bottom, the derivative of positive cosine is negative sine, all over bottom squared. So let's clean this up. 0 times cosine is 0. Negative 1 times negative sine is positive sine of x over, and I'm going to write cosine of x times cosine of x. I think you'll be able to see something a little bit better if I write the denominator that way. Isn't it true that I can write 1 times anything and get that thing back? So I'm going to write the numerator like that. The denominator is still cosine times cosine. All that's happened here is that we have taken this term and we have written it equivalently as the secant of x. We've taken this term and we have written it equivalently as the tangent of x. So we've proven it is true the derivative of secant is secant times tangent. You're responsible for knowing that. If you are the type of student that likes to memorize things, just memorize that. If you are the type of student that would accurately go from here to here, or if it were multiple choice, it would show up in that form. I don't care how you find the derivative of secant. You just need to do it correctly every time you find it, and you need to do it with as little time spent on it as is possible. We are taking a timed test, and so we don't want to waste time if we don't have to. Let's work this final example. Find f prime of x for f of x equals 5 times the sine of x minus 1/2 the secant of x plus x times the tangent of x minus 7x squared plus 3. This function has a lot of stuff going on. So f prime of x, I'm going to differentiate the first term. There is a constant or a coefficient that I'm going to pop out front, and then I'm just going to worry about the function I need to find the derivative of. The derivative of positive sine is positive cosine. Now I'm going to move on to my next term. Derivatives break up over plus and minus, so I'm just going to copy the minus sign down. Again, I have another coefficient or constant that I'm going to pop out front, and then just worry about the derivative of that term. The derivative of secant is the secant of x times the tangent of x. Derivatives break up over plus. I'm going to hop down here and put a plus. And I hopefully recognize that as a product. That is x times the tangent of x. So I'm going to have to apply the product rule here. 1d2 plus 2d1 just to get the derivative of that one term. So 1d2 plus 2d1. There's the derivative of just that one term. Copy down your minus sign. Now we have a coefficient or a constant we're going to pop out front, and we need the derivative of x squared. That's power term. Power pops down front, reduce the power by 1. I'm not going to write plus down because I recognize the derivative of a constant is 0. There is f prime of x. That's what they ask me to find. I don't have to simplify. I don't have to distribute. I don't have to do anything. This is correct. If they want to give me an x value and have me find the equation of a tangent line or do something else with it, I can. But if they don't ask me to, I never simplify. I just walk away.